Hello and welcome. In this video, we will be learning how to write proofs by induction. So the way this method works is that you will have to use your algebraic knowledge and use basic the base number. The proof has four stages. Stage one is the basis of the proof. Stage two is the induction hypothesis. And stage three is the inductive step actually. So stage three is the most challenging part of the proof, and stage four is basically just the conclusion. All right. So what does it mean? The basis step is just to show that you can. This is a hypothetical step ladder that you can get from ground level 0 to rung number 1 of the step ladder here. So that involves just substituting number 1 on the left hand side and right hand side of the expression and showing the left hand side equals to right hand side. I'll show you an example in a second. And then by inductive hypothesis, you say, all right, I'm going to make an assumption that what I've been told is true for some value k, and then the inductive hypothesis, that's the induction hypothesis, and you are going to prove that you can get from level k to level k plus 1 if the formula works from this step to this step, can take you from one step to the next, then as if the dominoes will be falling, so it can have a knock-on effect, and you just using the fact that by induction it will go on. This will prove for all other steps as well. This formula holds for all other steps. So let's have a look at one of the examples. So as I was saying, these are the steps. The basis step is to you just use number 1 in left and right hand side, and so on and so forth. So we will look at this example here. We've been asked to prove by mathematical induction that for n, this symbol means that n is a member of positive integers. So that means that 1, 2, 3, 4, not there's no number in between that can be accepted, and that plus sign obviously means that it's a positive number. So this formula is saying, if you remember from chapter 7 of pure maths, we can represent odd numbers with this form 2r minus 1 or 2r plus 1. In this case, they're using 2r minus 1. So you don't have to understand every formula, but this particular formula, this is sum of odd numbers. So first odd number is 1, which is a square number. The next number is 3. So 1 plus 3 makes 4, which is yet another square number. If we add the next odd number 5 to that, so I've drawn for you 5 squares outside, on the outside here. So that adds up to 9. So that's yet another square number, which is the sum of odd numbers in maths. They add up to square numbers. So the next number would have been a 7. I'm not drawing that perfectly there, but you understand that we had 9 up to here, and 9 plus 7 makes 16, which is yet another square number. So obviously this is not a proof. This geometric shape I've been drawing for you is not a conclusive proof. So we need to actually write this with algebra and go through the steps. I was just explaining for you that what this summation formula means if you are, well, this is if this is the first video you're watching about summation formulas. So we are going to go through this 4 stages. So the basis of this proof is to substitute number 1 on the left hand side. So you start by saying the left hand side means that when our n equals to 1 is going to be just sum of the first term, 2 times 1 minus 1, which is simply 2 times minus 1, which is 1. And on the right hand side, we also have 1 square, which is 1, and they match. So this is showing that the formula holds for 1, and that's great. Even though it's really basic and really simple, we have to write this stage. That's part of the part of the proof. Okay, so we went through the stages and we calculated the left hand side and right hand side for the basis step. Now we're going to make the hypothesis assumption. All right, so this is not difficult at all. All you have to do is change the value of n, use a different letter. You common letter we use is K. So you're just going to go and rewrite the formula with the letter K. And what does that mean? That means that the sum of integers up to 2k minus 1, sum of odd numbers up to 2k minus 1 is going to be k square. Okay, so you're matching this left hand side. So every time we will use this assumption in the next step, in the inductive step. This is very important. So when we want to evaluate this sum, we are going to use k square rather than writing all these integers and writing this summation. So we're going to make this substitution where we've underlined the blue k square. So let's look at the inductive step. So now here we are going to go for this sum. We are going to add the next term to the summation, which will be, we're going to replace that r, this r here, we're going to replace it with k plus 1. And so we rewrite the sum because we are going to go, this summation is going to go, instead of k, we're going to go from r equal to 1 all the way to k plus 1. So that involves us going all the way from 1 r equals to 1 to k, and with the same formula obviously, and adding one extra term. The last term in this formula will be the 2 multiplied by k plus 1 and taking away 1. So if I expand that bracket here, just above it, 2k plus 2 minus 1, that 2 and a minus 1 will give us a plus 1. So we will have, in fact, numbers 1, 3, and so on. I'm going to shorten them with dot, 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 and up to all the way to the last number, which involves 2k minus plus 1. So we said up to here, this form, the everything up to k, we can replace that. If we go back and look above here on the, we made that assumption that we had that summation. This summation is equals to k square. So we can rewrite this section, this summation, as k square. We're using our induction hypothesis, k square plus the 2k plus 1. Now you have to think carefully and see, obviously this looks like a quadratic form, so we can factorize this, and the factors of this are k plus 1 times k plus 1. So I'm just simply going to write k plus 1 squared. And that's it. If you notice, we had k squared in the inductive hypothesis, and now when we added one extra term here, we ended up with the same form, n squared, but that n there, we have a, because on top of this summation, we had k plus 1, now we have k plus 1 squared as a result of that summation. So the, every proof is different, but you have to at some stage think ahead, and you could almost cheat and think, okay, I had k in the inductive hypothesis that gave me k square, and I need the result and the inductive stage. I want my result to actually result into the same form but with a plus 1. So this is it. This is the crux of the lesson. So once we've got to this stage, all the algebraic work is done. We just have to write write a conclusion. So now in the conclusion part, we are writing basically that because the uh, summation formula held for k, and it also worked for k plus 1, therefore it will hold for all positive integers. Okay, so the conclusion part is to write that uh, because it held for k and k plus 1, it will hold true for all positive integers. All right, so let's have a look at yet another example. In this next example, we are going to prove the summation of R squares is this formula there. If you've done chapter 3 in further maths, you would have seen this in chapter 3 and 4. 3. So we are going to set up this proof by using first of all the basis step. So what is the basis step? Is to use a number 1 for n. So this summation from 1 to 1 of r square is basically 1 square. 1 square is 1, and under this is left hand side. So on the left hand side we have a 1. On the right hand side, if we substitute 1 in for n, we say our n is 1. So we will have 1/6 multiplied by 1 multiplied by 1 plus 1 multiplied by 2 times 1 plus 1, which is a 3. So we have 1/6 at the front multiplied by 2 by 3. So it's not difficult to see 6 over 6 is 1. Therefore, the left-hand side and right-hand side match perfectly. So that's the basis step done for this section. We are going to make the hypothesis step now, and make an assumption. The assumption is that the formula holds for value of k. So this is just to rewrite the formula, and instead of n, we're going to substitute letter k. And we are saying that sum of all square numbers up to k square adds up to that form, 1/6 times k times k plus 1 times k 2k plus 1. So this stage, I'm going to shorten this and put it on the top of the page so that we have room for inductive step. So now we are going to rewrite the summation, but instead of n, we will have k plus 1 on the top of this sigma's signature. So this means that using our inductive assumption that these numbers up to k square can be replaced with that formula up there. So this section can be replaced with what I've underlined on the top there. And we've added the next square number, which would be k plus 1. All right, so let's go through the work and we'll see. If I rewrite that formula there, so here we end up with this k plus 1 square. Now, if we want to be clever about this, we have to factorize some common factors. And I can see already that k plus 1 is a common factor. But unfortunately, because we don't have a 1/6 in front of this term here, k plus 1 square, we need to multiply it by 6 before we can divide it by 6. So the trick is to multiply it out and multiply it by 6 before we can factorize the k plus 1. Otherwise, it wouldn't make sense because the other k plus 1 has a factor of 1/6 in front of it. So this involves going through these steps of calculations, and now we can write the whole term over one denominator of 6, and now we can go ahead and factorize that k plus 1. So inside the square bracket, we'll have these blue underlining terms. And if you like to pause the video and make sure you've evaluated for yourself and it will make sense for you, then what we can do inside that big square bracket, we can collect like terms and see if we can factorize after expanding the brackets there inside the blue big square. So we'll have 2k square plus k plus 6k plus 6. So these terms will factorize, in fact, into yet another 2 brackets. So if you careful about this, you'll notice that you can factorize this as 2k plus 2, 2k plus 3, and k plus 2. So we've dropped the square brackets and put them over. And sorry, there's a 6 missing down here. Obviously, we do need that 6. Now, you say, okay, this doesn't quite look like this form. So what do we need to do? Well, we can still go ahead and manipulate. This 3 can be broken up, and we can manipulate this in the conclusion step just to show that everything makes perfect sense. So on the next page, I'm going to rewrite that, what we ended up at the end of the inductive stage. So this 2k plus 3 is in fact, can be written as 2k plus 2 plus, if I just put another step here for you, this is 1/6. This k plus 1 is rewriting that k with a plus 1. This, we can write this as k plus, this 2 is broken up to plus 1 and yet with another 1 after it. And this 2k plus 3 was originally 2k plus 3, but we can write it as 2k plus 2 plus 1 and factorize this 2 out of these two terms. So we have a bracket inside the bracket. So now you notice that this is exactly the form that we started with. Every one of these red brackets I've put here is the original, well, in the original formula was n here. So if you compare these last two, you notice that when we had n, we have k plus 1 now. When we had n plus 1, we have k plus 1 plus yet another 1. And where we had 2n plus 1, now we have 2 in front of this bracket here, which is representing our next term. That's why it has to be k plus 1. Okay, so if I get rid of my handwriting there, and it should make sense. So then you write for yourself, well, these are the terms that match. Therefore, if it held for n equals to 1 and it held for n equals to k, and it also held for n equals to k plus 1, therefore this formula works for all positive integers. All right, so let's look at the next example here. In this next example, we wouldn't need to evaluate these exactly one at a time, but for illustration purposes, I will show you. So you substitute in the basis step, one in the left-hand side and one on the right-hand side. 2 to the power of 1 times 1 is 2. The summation on the left-hand side is equals to 2 when we substitute 1 for n. And on the right-hand side of the formula, let's go through the calculations. 1 times 2 is 2, but the other bracket is equals to 0. Therefore, we just have a 2 as a result. So that's the basis step done. Then we have the assumption step. So in the assumption step, we will just replace the formula, rewrite the formula, and replace n with k. Notice these numbers, okay, these numbers will take some time to write and evaluate. You don't have to go up to the fourth term. I suppose in exam, when you're short of time, you can stop at the first and second term and put dot, dot, dot after that if you're absolutely bounded by time and you don't have the resources to calculate all of those. They are not totally necessary for the proof. The proof is mainly to show algebraic steps, how the algebra works. So then what we will have is, as a result of this hypothesis, is that the last term here is k multiplied by 2 to the power of k. So make sure you write that in your assumption step. The very last term is important. And then you will just write the formula with k replacing n. So we will use that. We will use that in this next step, the inductive step. So now in the inductive step, we are assuming the formula held for up to k. Now we're going to add one extra term, which is k. This you use this formula here, and you say, now I'm going to use k plus 1 wherever the r is. So inside this bracket, we'll have k plus 1 times 2 to the power of k plus 1. And we will add this term at the end of our summation. So we write this summation, sorry, that should be a k plus 1 up there on the summation. So then this was all the terms that were we had above in the assumption step. So we can replace these two underlining red values with 2 multiplied by all that bracket there that I'm showing with double underlining. So we are going to make this replacement there, and this last term remains as it is. Now, if you are careful with your expansion of this square bracket here, we can expand this square bracket, and what we end up with is this next line here. Now, instead of this expanding and rewriting this term here, we look and we say we have 2 to the power of k, and we have another 2 there. If you're careful with your index laws, you know that 2 multiplied by 2 to the power of k 2 times 2 to the power of k is simply 2 to the power of k plus 1. Okay, so we just using the fact that this 2 has an invisible 1 for its index, so don't forget your index rules. This multiplication results in that. So we're going to use this step here and rewrite this line one more time, and what we will have is a common factor of 2 to the power of k plus 1. When we factorize 2 to the power of k plus 1, what we will get inside the bracket is k plus 1 and k minus 1, and the plus 1 and the minus 1 cancel away, and what we end up with is just 2k. Now, one more time, if you careful about this, you can think about this formula here, and although it doesn't quite look like it at the minute, we can break this, factorize a 2 out of this form here. So once we factorize a 2 out of this last line here, we end up with this expression here. Although you don't see a 1 and a k minus 1 in this bracket, we do have the 1 at the front of the bracket, but instead of this k, we can write k plus 1 in the conclusion step. We can rewrite this as k plus 1 minus 1. And that plus 1 is just to show that we went one step ahead in this formula. So this is actually the same format that we needed to get from the right hand side, and we found that carefully. So this k turned into k plus 1, and the minus 1 simply follows it. So although you couldn't see that, you can always perform this trick in maths, add and subtract the same number, in this case 1, and you just to show that everything is working perfectly well. And the power of 2 also went one step up to k plus 1. So the statement held for n equals to 1, and also held when we went through the algebraic steps. So here we've proved everything worked perfectly well. So here's the example of the exercises, and if you like to pause the video and have a go at the first question, I went ahead and I wrote the answers by hand for the first exercise, and go ahead and pause the video if you don't want to see the answer, and here I'll show you the steps you need to go through to get the answer that you are required. There is a half in front of the last step that's not showing. So I hope you like this video, and I'll see you in the next video.